Okay, let's take a look at some examples where we will be verifying trig identities. Um, some of these are, they can look quite horrendous, but then simplify. So we'll look at that, but first I did want to take a quick second of explaining simplifying versus verifying. So this very first example is simplifying because I don't know what it ends as, right? I have this random, kind of long trig expression that should simplify down. And the more you practice these, kind of the more you'll see different techniques and different ideas of how to simplify. Sometimes there are many ways to go about them, and one might be shorter, but your way may be different than somebody else's. It's just longer, right? But we end in the same result. Verifying, on the other hand, means there's an equal sign, right? Look at these other two here, and I know the end result. I need to get one side of the equal sign to look like the other. All right. So let's begin with this first one. A few key things I put on the upper right too in blue is use your fundamental identities like the Pythagorean identity, sine squared plus cosine squared equals 1. Use your quotient identities like tangent is sine over cosine. Sometimes you'll need your negative angle identities, the even and odd identities, where sine negative x is negative sine x because it's an odd function, right? Where cosine is, and its reciprocal secant is the only even function. And the reciprocal identities as well, which we'll end up using here for secant and cosecant. Okay, so using the fundamental identities, a few other tricks that you'll encounter are these. So looking at this one, I'm going to change everything to sine and cosine, and I'm also going to use that even and odd function. So sine negative x is negative sine x. Now we had another negative out front though, right here, right? So negative negative, we could change that to a positive. Cosine x, there's really nothing to do, so we're just going to leave it cosine. Secant is 1 over cosine. Okay, and that's what I mean by changing them to sine and cosines. Often a complex problem, you change it to sines and cosines, it might look a little longer for a minute, but things will start canceling. And already I could see this, right? Cosine times 1 over cosine is going to cancel. Cosecant is 1 over sine, and I had that sine up front, which means those two would cancel. And now I'm left with just tangent. I'm going to go ahead and change tangent to sine over cosine. And then the denominator, we had cotangent, which is cosine over sine. All right, so I changed everything to sine and cosine. That isn't always needed, but often helps. Algebraic properties, including arithmetic here, right? Like we have two fractions basically, sine over cosine divided by cosine over sine. So let's change that. Division of fractions means to multiply by the reciprocal. So I'm going to multiply by sine over cosine. Right? We have to flip the denominator, the reciprocal of the denominator. And now I'd have sine over cosine squared, right? Sine times sine, cosine over cosine. And I know that sine over cosine is tangent. So one question is like, well, how do you know when it's simplified? And that's why ultimately I prefer the verifying identities, the ones with the equal, because you know the end goal. But we do need simplifying later when we go to solve equations. So it is important. So if you ended there, it's not necessarily wrong, but I would argue that tangent squared is a bit cleaner than sine squared over cosine squared, right? So that ugly mess we started with reduces all the way down to tangent squared. Next one. I wanted to throw a quick, semi-easy identity here. So I want to talk about this one because sine squared plus cosine squared equals 1. But sine plus cosine squared, right, in parentheses, is not 1. Remember that this is not sine squared plus cosine squared. You cannot just distribute that square in there. Okay, it doesn't work. You're forgetting the middle term. So let's write this out. If you don't remember the formula for sum of squares like this, okay, if you don't remember the formula for that, that's fine. Just write it out, right? Where sine is A and cosine is B, basically, right? We would have this. And now FOIL, we'd have A times A squared, which is sine squared, A times B, AB, B times A, which is another AB, and then B squared, which is the cosine squared. So what we were missing, right, if we tried to just distribute a square, is this AB plus AB, or 2AB. Sometimes working with trig, we use a substitution and create it algebra to kind of help. I don't think it was needed in this case, but sometimes it does help. Think of a u substitution, but right, I can't let u be sine and cosine, so in this case I chose A and B, but it really doesn't matter. So squaring sine x plus cosine x squared, I would get sine squared plus 2 sine cosine plus b squared, which is cosine squared. Okay, anywhere there was a, we're just writing sine. Anywhere there was a b, we're writing cosine. Right, so sine squared, cosine squared, and then 2 sine cosine. Well, our end goal is to get what we have over here. And sometimes it takes manipulating both sides independently, but what we cannot do is combine the two sides. We are trying to show one side equals the other, and it may take multiple steps. But essentially, we have it. We are done because sine squared plus cosine squared is the Pythagorean identity, right? Those two combined make 1. So since those are 1, and then we have this 2 sine x cosine x, both sides are equivalent now. What I'll often do if I'm only dealing with one side, and remember all of this in here was scratch work, right? I was explaining it. So really I had first line, line 1, the problem, line 2 was here, and then line 3 I'm done. But sometimes what I'll do if I'm not messing around with the right side, I'll just do that. That way, right, I'm saying ditto. I don't need to rewrite the whole thing all the way down. And at the last step, I mean, we do in fact have the same thing. So we are done. Sometimes what upper division math starts to do is they do these 2 little slashes right there, or they'll write QED. Either way, it means like what you were trying to prove, what you're trying to show is done. All my steps are done here. I forget what QED is in Latin, but same thing. All right. I have 2 more complex examples here. They could perhaps be done differently than I do it. And so I'm just going to take the approach that I see first, which I typically use sines and cosines. That's my common go-to, especially in this one because I already have cosines and sines. I just need this tangent rewritten. Now, obviously, I'm not going to manipulate the right side to look like the left, right? We could, but I don't know how I would even begin that. So I'm going to change tangent to sine over cosine. So we have cosine squared minus sine squared, 1 minus sine squared over cosine squared, okay, equals, and it's almost like a question like, does it equal? Well, yeah, I'm trying to show it, but I don't know that it for sure equals it yet. And I know cosine squared really wasn't a lot to write, but that's okay. I'm focusing in on the left side. Okay, well, what to do next? I don't like fractions over fractions, so what I prefer to do is let's clear this fraction. Okay, I'm going to multiply the numerator and denominator by cosine squared. That way when I distribute here, let's use blue, I guess, these would cancel, right? But I still need to distribute here. In the numerator, just because I'm kind of looking ahead, I'm going to leave it. And sometimes that is the best bet. Leave it factored. Maybe you'll get lucky and things will cancel. So I'm going to leave this as cosine squared multiplied by cosine squared minus sine squared. Another key thing, sine squared plus cosine squared is 1. Cosine squared minus sine squared is not 1. Right? It needs to be plus. Over. So we distribute the cosine squared to the 1. And then when we distribute it here, right, they cancel, so we get sine squared. And look at that. I can reduce, I can simplify the cosine squared minus sine squared because it's a product in the numerator, and in the denominator, that's all I have. Right, so these terms cancel, and I'm left with only cosine squared on the left and cosine squared on the right. Okay, done. Is there another way to do that? I'm sure you could. That, again, changing the sines and cosines is oftentimes the best approach. All right. Last one here. Again, I like sines and cosines, but I'll take a different approach. Let's try something else. So if you chose to do this, I'll just write the first step with sines and cosines, right? We would change everything. I would go secant is 1 over cosine, tangent is sine over cosine, cotangent is cosine over sine, and then I just have this cosine. And now, you know, the left side is ugly. That's probably what we're going to end up changing, but you can work with both sides at once. Like secant is 1 over cosine and tangent is sine over cosine, right? Maybe it'll help to kind of think of the right-hand side as we go with the left-hand side. But like I said, I'm going to try a different approach. Sometimes we want to actually incorporate the difference of squares. Okay, that was one of my hints here. If you don't know what to do, try that. And the reason it's going to be helpful in this case, let me go ahead and rewrite it to give myself some room. And I'm going to leave the right side for now. So I'm going to multiply by secant minus tangent. Secant theta minus tan theta. secant theta minus tan theta. So let's just distribute the numerator. We have a difference of squares, right? Which means the middle terms will cancel, and all I need to think about is first and last. Secant squared minus tangent squared. That's not directly one of the identities. Okay, we have the Pythagorean identities, and we have talked about how to get this changed. If we divide everything by cosine squared, we would end with 1 plus tangent squared equals secant squared. Okay, that's another Pythagorean identity. But just because it looks like that doesn't mean we can't manipulate it, right? If I solve for 1, if I subtracted tangent squared, now I know that this expression here is just 1. So on the next line, that's what we'll have, but let's go and work with the denominator. All right. Now, I did this way to show how we could start manipulating difference of squares at times, and also that we do that because we hope that it turns into a Pythagorean identity, which in this case it did. Okay, so denominator. We have cotangent times secant. I don't know off the top of my head what that would reduce to, cotangent times secant. But thinking of cotangent as cosine over sine, and secant is 1 over cosine, right? Now I know when I multiply those two, because I'm foiling, cosines would cancel, and I would just have 1 over sine, or cosecant, right? So that's a lot to kind of digest all in one step. So let's go ahead and just leave it at that. Cosine over sine multiplied by 1 over cosine would leave me 1 over sine. Okay. Cotangent times negative tangent, that's just going to be negative 1. When I distribute here, that's going to be negative 1 because they're inverses of each other. Right, so minus 1. Cosine times secant, so secant is 1 over cosine, so those cancel, and I get plus 1. Cosine times tangent, tangent is sine over cosine, so the cosines would cancel, right, and I would just get sine. Alrighty, now let's go ahead and finish simplifying. I see a pair of 1 and negative 1 that can cancel. As we discussed, the numerator secant squared minus tangent squared is just 1. So now in the denominator, I just have 1 over sine, or plus sine, sorry. And if we got LCDs, so let's go ahead and, I do need the right side. If we got LCDs, or how about let's just multiply by the LCD, which is sine. Okay, in the numerator then I have 1 times sine theta. In the denominator, those would cancel. I'd have 1, and then I would have sine squared. Now remember, I'm trying to get secant tangent, right? Secant tangent's my goal. I don't see it yet. Maybe you want to change secant tangent. That's an idea. Let's go ahead and do that. I'm not sure. I'm not seeing it right away. So secant is 1 over cosine, and tangent is sine over cosine. So if I had sine over cosine squared, I would be good to go. I think, oh, I see it now. I messed up on a negative. It's actually right here. Right? And I'm not going to redo this video. I'm human. It's okay to make mistakes. I do it quite often. Usually it's something dumb like that. I had positive cosine times a negative tangent. Right? So that negative, even though the cosines cancel, I had negative sign. So therefore this was a negative sign. And 1 minus sine squared is cosine squared, actually. So, right, because here, if I subtracted sine squared, right, it's a Pythagorean identity. Just because I have sine squared plus cosine squared equals 1 doesn't mean I couldn't say cosine squared is 1 minus sine squared, right? You can manipulate those all you want. So now on the left, I'd have sine over cosine squared. And on the right, I have sine over cosine squared. Done.